John Dorsey leads a team here at LARC that is developing new concepts and technology for long-reach, tendon-actuated planetary surface and in-space manipulators. Mr. Dorsey has a patent and has published 57 papers. Please welcome Mr. John Dorsey.
Thank you. Hear me? Okay. Okay. Yes. So I'm going to talk about long-reach manipulators, and I just want to point out that the work that I'm going to talk about is actually being funded under the Space Technology Mission Directorate under Game Changing Division. So this is funded technology work. And in this case, this is just one of many examples, but it's a generic technology for long-range manipulators, and we were asked to apply our concept to the asteroid retrieval mission and just see what we could come up with. Long reach, in our definition, is something like a station or a shuttle class RMS. So we're talking about a 50-foot reach or more. I think Keith showed you a lot of slides that pretty much prove that long-reach manipulators are something that NASA finds very useful. On shuttle, they were used for station assembly. They've been used for Hubble servicing, other satellite servicing. Currently on station, they're used for berthing, docking, and other types of operations. So the state of the art is the shuttle and space station remote manipulator systems. So you see an example here, recent use of the station arm where it was docking the SpaceX Dragon to the station. Unfortunately, there's some not only limitations to this current technology, but if you look at how these arms go into space, they were all launched on shuttle. And since we no longer have space shuttle, we cannot put another arm like this in space. We've lost that capability just to even launch these kind of systems. Another problem in terms of when you start applying, I'll call this a conventional robotic architecture, where you have these fairly long booms. These are about 20 feet, 25 feet long, and then conventional robotic joints, which are motor drive gearbox systems. So it turns out that most of the mass of this system, say out of a 900-pound robotic arm, 800 pounds are in the joints. Only 100 pounds are in the structure. That's kind of that gives you an idea. So that becomes a problem. They also have fairly high compliance, which in some operations are good and some operations are bad. One of the problems a conventional robotic architecture with the massive joints leads to is, since it costs so much weight to add a joint to the robot, it's not something you want to do, especially if you have to launch it. If you think about how we want to launch robots in the future, they're going to go up on a Dragon or some other kind of vehicle. We really want to package them tighter. We want to add more joints, if for no other reason. I mean, we would like the increased dexterity, but you also want to do it for packaging reasons. I can't sit there and add 400 pounds every time I add a joint to the structure just for packaging. So the conventional architecture really has a lot of limitations. What you see up here now is, and I'll have some charts where we'll go into some of the details. This is actually a shuttle class manipulator. In other words, it's about 50 feet long, attached to a space vehicle, and it's berthing to an asteroid. But our goal in developing this technology was and essentially make a shuttle type arm the minimum reach. And so we could extend the reach of the systems. Because we have lightweight joints, we can increase the dexterity, increase packaging efficiency, and structural efficiency. So I'll go through all these. The basic concept is shown here. It's actually a tendon actuated structure. So it's where you have these tendons here oppose each other and actuate a hinge joint. So it's very similar to what we have in our fingers. We actually have tendons on each side of our knuckles, and they pull back and forth, and we articulate our fingers. This just happens to be on a much larger scale and a little bit of a different architecture. It's very lightweight because we've got essentially these very efficient compression trusses, compression members, and cables. So from a structural perspective, this is about as light as you can get. The way we achieve the high joint efficiency is by these cables that do the articulation about this hinge joint. If you think about generating a moment, the force is generated by the cable, the offset distance is generated by what we call the spreader, the torque is the R cross F. I get a very, very high torque value just by pulling on these tendons because I have this offset distance. Because I can do that, I can end up with much smaller motor and gearbox systems and a much lighter weight system to achieve the articulation. In addition, we get stiffness out of the same tendons that do the actuation. It's kind of like a suspension bridge. So it actually adds to the stiffness of the system as well as doing the articulation. Some of the novel features, it's a very versatile system, just the idea of trusses, a hinge joint, and cable actuation. There's just a lot of different control schemes that we can use to control the robot. There's also different kind of structural architectures that we can generate, different operational things that we can do with it. This just shows 1, 2, 3 link system where we have this idea where as the arm articulates through its range of motion, you can either force the cables to stay attached to the spreader, which starts restricting your force capability as you get larger and larger angles. Or you can allow it to lift off of the boom and you maintain a much larger force as you do that. Of course, that gets in your workspace. But it's something that you can trade off. You can also attach these cables not just at the ends of the booms, but at different locations on the booms for whatever reason you may choose to do that. You can add additional spreaders to the system so that you keep the cable offset through a wider range of motion without requiring liftoff. This is just some of the things you can do, but there's a whole slew of design features. One of the most innovative things, and we have applied for a patent on this, has to do with this actual hinge joint in the middle. This robot, we can get a full 360 degrees of actuation at this hinge joint. And as you add joints to the system, obviously the dexterity of the robot just increases hugely for every joint that you add. But here's an example of this system. It's packaged up for launch. So each of these links is about 12.5 feet. And just two adjacent members would look like this with the hinge when it's packaged. And as you deploy it or articulate it, this member is going to rotate about 1 hinge joint, and as it rotates up and then all the way over to give you this configuration, you can see this is what the hinge joint looks like, and then it rotates about another hinge point and folds up the other way. So this gives us the very compact packaging that we need, as well as the full articulation range of a single degree of freedom hinge joint. Just one of the many novel features of this. Why a manipulator-based system? Well, you've seen slides that show option A and option B in this asteroid mission, and what did you see? 2 completely different systems. NASA's notorious for single-point designs, and that's an example of that. You saw in a couple of the presentations all of this uncertainty. There's uncertainty before you go out there. Am I going out and going to find a 2-meter object, a 5-meter object, a 10-meter or 20-meter object? You're not even sure what size it is. You don't know what shape it is. You don't know what the rotation rate is. You don't know if it's a rubble pile. You don't know if it's a big rock. You don't know if it's iron nickel. There's all this uncertainty. The idea behind a manipulator-based approach is that manipulators are kind of like the fingers in our hand or our arms. We have a lot of capability, and if you take a very versatile system, like a hand with the fingers on it, and give it a wide range of tools, then I can go out on a mission and handle uncertainty. So the idea but really behind the manipulator is to allow us to handle a lot of these uncertainties that you saw mentioned by some of the previous speakers. And that includes the free-flying mission, all the things. I'm not going to read this. I think I talked about most of them. But essentially, with the same system, we can do either mission A or mission B, and I'll just show those in the next couple of slides. One thing we have to think about is this is, the Atlas V with a long or medium shroud is the launch vehicle that we're kind of working to put this system together. So you see the SEP spacecraft here. that everybody's talked about. And this embodiment, this is the bag. By having the manipulators, I'll show you what the manipulators do with the bag. We've eliminated all the deployable, inflatable booms and cable systems. We have a very, very simple bag. It's basically a trash bag that the robot deploys, cinches shut, and that's all it has to do. So we've simplified the bag by using robotic manipulators too. And so because we've simplified it, it packages in a very, very small volume. The arms, there's 3 arms in this system. As you go around kind of the circumference of the spacecraft, they're spaced at 120 degrees. And they fold up, and this just shows that, yes, you can fit in the medium shroud with this system or the long shroud. So we've achieved the packaging. Just some more details. Another note, our technology is being developed under Human Robotic Systems. We also have a technology project that's been developing materials and concepts for inflatable structures, inflatable habitats. It turns out those same soft goods structures is what we would use in this simple bag. So we're already developing the technologies within NASA to do the mission the way I'm describing it. This just shows another view of the system, I think. So we have 4 truss links. It turns out this one was sized to grab at the time, I think it was a 17-meter boulder with a potato shape out of free space. So we kind of looked at, it takes about a 20-meter manipulator with 4 or 5-meter links to kind of wrap around that thing, given a bunch of different possible configurations you may encounter when you get to it. And it's 5 degrees of freedom. There's 4 hinge joints, single degree of freedom, and then a base rotary joint. Soft goods, it turns out, is a very, very simple system, so I'll show that here. So you've seen some of this before in previous presentations, but the spacecraft kind of comes up to, here's an egg, big old egg out in space. And the first thing we do is we deploy our 3 big robotic arms. So these are 20-meter arms after you deploy them. Here's the bag sitting right here. Depending on what you see, this is an example of if you have to, if it's more of a rubble pile and you really have to enclose the asteroid before you even want to grab it, you have the option because Carlos has parked us in that thing and we're kind of like, we're in an attitude where everything looks like there's no relative motion. So we can just deploy the bag around it as we show here. The arms pull the bag out. Once you get to the end of it, you cinch it shut. Then you can grab this thing around the bag and you can pull it into the spacecraft. You can adjust the CG so it lines up with the thrust vector so you don't get any offsets when you come home. This is an example of if it's a more of the iron nickel class where you actually grab it first, 3 fingers, we grab this thing, you hold on, and the spacecraft does the de-spin operation, and then they still want to enclose it, so then after we do it, we deploy the bag and bring it home in this scenario. If you're going to a large asteroid and you want to pick up rocks, that's depicted here, think about this. Right now there's an arm on station. Station's a big structure, so that's the big rock, big asteroid. And Dragon comes up and the arm grabs Dragon and berths it to the station. In this scenario, you can envision Dragon having an arm on it and it comes up to the station and it berths itself to the station. Same scenario, with one arm, you can berth yourself to this large asteroid. You have 2 more arms to pluck rocks off or do whatever you need to do, fill up a bag. We are developing this technology, like I said, in our robotics project. This is the first generation, so you can see it looks a lot like those pictures. Here's the truss, here's the cables, here's the tops of the spreaders, here's the motor gearboxes, here's our zero-G simulation system. More recently, we've built a flat floor facility to do zero-G simulation over in building 1293, and we've moved our manipulator work over to there. This is actually an air-bearing floor, so now this thing is mounted on air bearings. This is a spacecraft. We're going to have 2 arms to it. This is going to be an asteroid. So within this facility, we're going to be able to demonstrate things like asteroid capture with robotics, as well as satellite servicing, all these different technologies. So hopefully, in summary, I've shown you that we have a new concept that overcomes many of the limitations of what I'll call the state-of-the-art shuttle-type arms. That this concept is indeed very versatile, and that same concept can be applied to a lot of different applications, and we're doing that. The operational versatility, I think, addresses a lot of the uncertainties in the asteroid mission.